Hi, I'm Jiaji, a postdoc from MIT CCL. Welcome to the presentation of Xstrings 3D printing cable-driven mechanism for actuation, deformation, and manipulation. It is my great pleasure to presenting our team from MIT HCI Engineering Group and Zhejiang University. Cable-driven mechanisms are truly fascinating. They work by threading a cable through multiple components, ultimately connecting to the end effector. With a simple actuation, user can achieve highly precise, real-time motion with minimal delay, making them both efficient and responsive. Their inherently lightweight and flexible nature make them indispensable in robotics. They play a crucial role in robotic designs, enabling precise spatial positioning, efficient object grasping, and love-like biomimetic motions. To simplify the design process of this complex mechanism, researchers in HCI and graphics have developed advanced optimization algorithms. For instance, Mueller and Shuyue from Disney Research introduced optimization-based methods for the inverse design of cable-driven kinetics wires and chains. To achieve task-specific designs, Lee developed an algorithm that translates the desired motions into cable-driven structures, providing our community with solid solutions from digital world. However, despite the sophisticated algorithm providing with a well-structured blueprint, building a cable-driven mechanism in real world remains highly challenging for non-experts. First, assembling a complex, movable structure is already a demanding task. Then we must carefully thread dozens of cables through hundreds of tiny holes and securely attach them to a specific end effector. Finally, achieving precise motions requires adjusting the tension of each cable to ensure balance and stability throughout the movement. To address these challenges, we present Xstrings, a method that enables 3D printing cable-driven mechanism for one-step fabrication. This method prints cables using nylon material while controlling G-code to preventing adhesion with PLA. As a result, no assembly is required. The moment it comes off the printer, it's ready to transform. Xstrings supports 4 types of cable-driven interactions: bending, screw, coil, and compress, activated by input force on cables. This primitive can be linked with 2 different combinations, series combination and parallel combination, and provide design space for embedded actuations and irregular shapes. To simplify the design process, we also present a tool that allows users to embed this mechanism in objects by automatically placing cables and joints based on desired behavior of the objects. This approach automatically creates cable-driven mechanisms without long production times or manual labor while maintaining their positions. The one-step printed tentacle consists of 3 key primitives, 2 bending primitives at bottom allowing movement in 2 different directions, and 1 coiling primitive at top. This unique combination enables the tentacle to efficiently locate and grasp objects with accuracy. In the applications, we showcase more Xstring samples including dynamic wall sculpture, a self-actuated bird claw, and a biomimetic lizard robot. Please enjoy. In conclusion, this paper Xstrings provides an automated one-step fabrication approach for 3D printing cable-driven mechanism with zero effort of manual assembly. We also developed an interactive design tool embedding mechanisms into a target geometry with 4 different motion options. We provide the results of technical evaluations to explore the properties of printed cables, including fatigue limits and the maximum tensile strain. We showcase a variety of 3D printed applications including gripping devices, bionic robots, and dynamic prototypes. I have spent years on 3D printing dynamic structures with bio-inspired properties, from hair to skins and to bones. And I personally still have tons of passion on it. I try to control the compliance of 3D prints with bridging structures, which is X-Bridges in WAIS 2022. And in 2024, we developed the thickness and softness of bridging structure to next level of only 0.04 mm in diameter, which is exactly the scale of a human hair. I also explored the kinetic mechanisms which are spatially articulated. Our prints can literally work with one-step 3D printing. Xstrings is my latest research combining the soft and rigid mechanisms, and it starts to actuate 3D prints just like the tendons in our hands. In future, there are still thousands of mechanisms that could be 3D printed. We could 3D print conductive material as a nerve system in 3D prints for sensing, and we can also print shrinkable materials as muscles for actuating. And there's also possibilities of printing self-healing mechanisms just like our cells. Thank you for watching.